So we're not only going to be dealing with kinematics or motion, but we're going to look at, this is big, right? Oh, come on, would you please write the relationship of what? Of motion to forces, okay? So we've been talking about what? We've been talking about acceleration. We've been talking about velocity, speed, okay? Of course, displacement. You can't have neither one of those if you don't have displacement. And of course, you know it's occurring during a time interval. Okay? It has to be. So, when we apply motion to forces, we produce what is called dynamics. Now, when you go into engineering, many of you will take classes on most all of you should have, unless it's, I'm not sure that you actually need statics and electrical or not, but you'll take a class on statics where all you're going to look at pretty much is forces. Newton's second law, Newton's third law. Of course, his first law goes without saying. And they actually, when you study forces and look at forces, they actually all apply in most all situations. They're a combination of all three. Okay. Now, it's not to say we can't have, you can't just say, okay, well, this is an example of Newton's first law and this is an example. Yes, you can. But in most applications, we see where they're a combination of all three. Now, of course, it goes without saying Newton derived these laws, and it's pretty interesting. He always said about himself that he stood on the shoulders of giants. So he took what other folks had already done, Galileo in particular, and built his laws from what Galileo, from what Johannes Kepler had done. And it's really interesting, too, when you look at what Galileo said, you look at what Johannes Kepler said about planetary motion, they all line right up. And so Newton took their work and developed his laws of motion. And he didn't actually do it from acceleration standpoint. He actually did it from a momentum standpoint. And we'll look at that later. He actually derived them from looking at mass and velocity. And derived, because what is the derivative of velocity? Acceleration. So he did it with momentum, which is practical. Okay, now, let's move on. All right, so how do we define a force? It's really simple, y'all. It's not that big a deal. A push or a pull. Woo, boy, that was a hard definition. A push or pull. So anytime we have interaction with objects, we're applying forces. And I always like to use a chair because this is something common. Okay, I pulled on the chair, I applied a force. I pushed the chair, I apply the force. Okay? And notice when I apply the force, notice the direction of my force and notice the direction the chair moved. So what would we deduce from that? That it will do what? That's exactly right. So when we apply a force, when a force is applied, the object moves in the direction of the applied force. Okay? It moves in the direction of the applied force. Now that's really general. That's a general statement. And y'all, come on, y'all, that's common sense. I mean, really, Mr. Shields, that's forces. Yeah, it really is. Okay, anytime you apply a force to an object, and really later on we're going to look at it from work standpoint. It's actually easier to study, and you'll do this in engineering, you'll actually look at a lot of problems from an energy standpoint more so than you will, well, what's the acceleration? Well, what's the velocity? You'll look at velocity more so probably will acceleration, but you're going to have energy. And let's say, okay, now let's solve this thing from an energy standpoint, because it's a whole lot easier, because what is energy? Well, it's the amount of force applied through a distance. Okay, and we'll get to that later. So even though force deals with acceleration, okay, it's easier to look at it from an energy standpoint. Now, and momentum too. Okay. Now, so we have what's called a normal force. So, all right, so we apply force, and what happens? What happens? We have what's called a normal force, and they say there's 4 types of forces, and I do want you to know these. Your first one is the normal force. A normal force is a force that is perpendicular to the surface. Real simple term. Please write that down. It is a force that is perpendicular to the surface. Okay. Now we'll get to Newton's first law here in a little bit. Second law, excuse me. By the way, what is his first law? Well, we'll get to that in a minute. Let's hang on. Good time. All right. Let's not get too much at one time. I don't want to choke you. All right. And I think hopefully, please Lord, you'll like this better. I like forces. I'm not saying I don't like the kinematics, but okay. All right. So it's perpendicular. So your laptop has a normal force that's perpendicular to the countertop. And it's always, notice, it's perpendicular. So if we're at an angle, it's still perpendicular. Perpendicular to the surface. So don't let the angle think that you still don't have a normal force. You most certainly do. And later on, we will look at how the angle comes into play. And yes, you know we're going to use trig. Okay. You have frictional forces. Now, come on. A friction force is a force that is what? It is parallel to the surface, but it's what? It's actually opposite in direction, isn't it? And notice they call that a contact force. So if I apply force in this direction, and by the way, when you say C-F-A-P-P, that's force applied. My frictional force is always going to be in the opposite direction, right? I mean, come on now. When I walk on the floor, let me ask you something. Do your shoes ever wear out? Well, sure they do. Why? Friction. Every time you take a step, the contact force between the bottom of your foot and the ground is in which direction? Well, you hope it's which way. If I'm walking this way, which way do you want the frictional force to be? Opposite. Because if it's not, I'm going to be doing some funky moving, right? You follow me? That makes sense, don't it? I mean, come on, guys. I know this is real, like, simple stuff. It's like, well, you not got anything better than that? I mean, come on, y'all. This is real stuff. And when they design shoes, they look at all that. You're going to be working on, if you're going to be moving a lot, if you're working in, say, I don't know, UPS, you're in the warehouse, they want you wearing good shoes. They don't want you slipping and sliding because it's a concrete floor. So I guarantee you they have a company they buy shoes from that have shoes engineered for where you're going to be working. Post office, I'm telling you, I know what I'm talking about. And you don't think about stuff like that, but yeah, they engineer shoes to grip slick floors. They don't want people sliding down and getting hurt and suing them. Okay? Yeah, that's frictional force. Sticky. Opposite direction, okay? All right? Then we have tensional forces. And I love tensional forces. Okay? Tensional forces. Now, notice they put an angle on this. All right, let me ask you something. Where do I get maximum force? Well, now wait a minute. Think about it. Think about your trig here. If I get down here, eye level, and I push 0 degrees, what's the cosine of 0? 1. So if I apply 5 newtons of force to this chair, how much force winds up being applied? What's the cosine of 0? 1. 5 times 1 is 5, okay? If I come up here to, oh crap, what's cosine of 30? 0.5? Is that right? Or is it 0.8? Dang, I forget my trig. 0.5, that's what I thought. Did right. Okay, good. Whew, pretty good for Monday. All right, now, if I apply that force at a 30-degree angle, how much force winds up being applied? 2.5. Okay? Now, we're not looking at X and Y. We're just looking just straight out the gate. All right? We'll get to components later where we got stuff pulling on each other. Okay? So if I want to apply maximum force, I need to what? Do it either straight up or straight out. Right? Unless I have an inclined plane. Why in the world do I want to use an inclined plane? Well, if I got to go up, do I want to go over, which is easier? Push it up a ramp or pick it up? How much work am I going to have to do? How much force am I going to have to apply if I pick it up? Maximum. What's the sine of 90? 1. I got to use maximum force. If I push it up an inclined plane, well, I don't have to use as much, right? That's why they use inclined planes. It's called mechanical advantage. Have you ever thought about that? You ever gone in these warehouses, there's ramps and stuff around? Now I know they use tow motors and stuff, but they do use physical labor too. They got ramps. Some of them are real long too. Well, why are they real long? Well, if they have to go up fairly high, they want a long ramp because it increases the mechanical advantage. Okay? Yeah. And if you're using a tow motor, the tow motor don't have to work as much. Don't burn as much fuel. Okay. I'm getting way on out there ahead, but that's okay because it's still force. It comes back to force. All right, now, so we got tensional forces. Everybody understand tension is pulling, and it can be, typically we don't look at tensional forces as pushing. It's pulling. Elevator hanging. Okay? Tensional on the cable. Red lights. Now, all right, you civil engineers, all right? Red lights hanging on the cable. How do I know what size cable use? Well, how much does a red light weigh? Okay. Well, you have to look at that. Well, do you want it to hang straight or do you want it to hang, how do you want it to hang? Well, you got to look at your forces, but they're going to be in X and Y direction, and you got to make sure the tensile strength of that cable is strong enough to hold up the force of gravity pulling on that red light. And what if you got 2 red lights? Well, here we go, You'll be doing problems like this. Okay. All right. And we're going to actually do some red light problems. Weight. There's your 4th one. Is that the 4th one? Yeah. Weight, y'all, is weight. It's the force of gravity. The force of gravity. Now, I know I haven't given you any equations. We're getting there. Just chill. We're getting there. All right. But I'm going to make it sense so far. We got 4 forces. We got normal. We got what? We got frictional. We've got tensional. And we've got weight. Right? Weight is how much you weigh. You ought to know that. We all ought to know that. How much force of gravity is pulling, the acceleration of gravity is pulling on my mass. Do not confuse weight. Oh boy, I'm going to write this down. Weight, and you already probably know this, is not equal to mass. Weight is a force. All right, now, boy, we're going to get technical here. Mass, now, here's a 9th grade physical science definition. Mass is defined as how much matters in an object. Well, we kind of lied to you when we told you that in high school, because that's really not. Mass is actually defined as the amount of the change in inertia. In other words, how much change in inertial velocity. In other words, it goes back to change in velocity is acting on an object. It's really what it is. You're looking at the change in velocity, the inertial change. Okay? How much, when you put something on a balance, how much does it move? Well, that's changing its inertial velocity from 0 to whatever. That's really what mass is. It's really to say amount of matter in an object. Does that affect it? Yes, but that's a very general definition. Okay? So we're actually looking at inertial. Okay? All right? We're looking at inertial change. That's why when you go to the moon, the amount of inertia doesn't change. In other words, the tendency to resist change in motion, your inertial mass doesn't change. You go to the moon, you still have the same mass. But gravity, your weight, changes. Your mass doesn't change because inertia is inertia, y'all. Inertia is resistance to change in motion. Okay, all right, now. Okay, now you don't have to write this down. But again, here's just some magnitudes of common forces. Now look at this. Good Lord, a blue whale. All right, pulling force of a locomotive. Are you kidding me? No wonder they destroy a car when they hit it. But really, we don't look at forces. We're not really looking so much at the force. We're looking at energy. Crashes, when they look at crashes, they look at velocity and energy. How much energy was there in the collision? Okay. All right. Weight of a 250-pound linebacker. Any of you played football? There you go. What's popping them pretty good, y'all. Weight of an apple, 1 Newton. Okay, and so on. Notice this right here. Electric attraction between a proton and the electron in the hydrogen atom, 10 to the negative 8th. Okay, gravitational attraction between the proton and electron in the hydrogen atom. Good grief, look at that. Yeah, how do they even measure that? I mean, come on, y'all. That's crazy. Okay, there it is. Now, all right. Now, very important, y'all. Boy, Heidi, I've said this, I've preached this till I'm blue in the face. You've got to draw these problems. You've got to draw them, and you've got to label them. Okay? So if this was me, I would come in here and draw my X and Y axes. X, Y, Lord of mercy, X. We apply a 2 Newton force at an angle of 30 degrees. Okay? All right? We're not going to receive the maximum amount of force because it's at an angle of 30 degrees. We're going to take the cosine of that number because we're pulling it in the X direction. Okay? We'll find out how much force we wind up with. Okay? All right. And we'll work some problems like that. The superposition principle of vectors. Now what does this mean? All right, what does that mean? We're just adding vectors. Adding vectors. That's all it is, y'all. Superposition principle is just the adding of the vectors. Notice when we pull on this box, we've got forces in the Y, forces in the X. Oh, me. Yeah. That we have to take into consideration. Okay? And so we have to do the sine and the cosine for these forces. Okay? And of course, the sum of them are equal to what? The resultant. You know that from doing vectors. Okay? Any questions on that? So we got to draw. We got to draw and we got to draw. We might try to work one problem today, and I'll show you what I'm talking about. I've already worked a few, and I'm not going to, well, I may go ahead and assign you some to be looking at. Okay. Okay, now, here again. Now, this is teaching us how to do this, and that's why I'm showing you this. So if you're still not sure how to draw, go back to the PowerPoint and look at how to draw these. We're pulling on the box. Now here they put it on an incline, but we're pulling on the box. We want to pull it straight up the incline. So draw your X and Y vectors. There's our resultant. There's the force applied, but what is the force in the X direction? What is the force in the Y direction? Okay? We call those our components. That should not be unfamiliar to you because we've already discussed components in chapters 1, 2, and 3. Okay? Now, so we draw it, and what do we come up with? We come up with what? We come up with what's called the resultant or the net force. Please write that down. When I say net force, what am I talking about? I'm talking about the resultant force. Okay? Very important that you get that. That also refers to something called what? the vector sum. You see that right there? That means the sum of all forces. Period. When you see that, what Greek letter is that? Sigma? Is that sigma? Yeah. Yeah. Or epsilon. Epsilon, excuse me, yeah, epsilon. Sigma is the horseshoe, right? No, that's omega. Omega's a horseshoe. Oh well, all right. That means the sum of all forces. The sum of all forces. So what does that mean? We got to add them up. 1, 2, 3, 4, 5, 6, how many ever you got. You can have 10. You can have 20. Now, dear Lord, let's not put one on there with 20. 2 or 3, 4 maybe. 2 to 3, let's keep it that way. All right? But you could do it. Because what are you going to do? You're going to do the components. You're going to do the X, you're going to do the Y. Right? Uh-huh. Now, notice this right here. Newton's first law. Boy, this is hard. Come on now. When a body is at rest or at constant, did you catch that? Constant velocity. Constant velocity. Boy, a siren ought to go off in your head. Woo, woo, woo. All right, what does that mean? What's going on with acceleration? Nada, that's right. Niet. Nein. None. Zero. Nein means no in German. All right? Uh-huh. So we're at equilibrium. So Newton's first law, there it is. Newton said that an object at rest has zero force, 0 newtons. That's not on. It's not on like Donkey Kong, all right? It's 0 newtons, all right? It's 0 newtons. Why? Because there is no acceleration. Now, I did not say there's not velocity. There is constant velocity. Folks, you have got to remember this. You've got to, I don't know what you got to do to remember it, but you got to remember it. Write it on your formula card. Please. And y'all, I'm not trying to be ugly or anything, but just you got to remember this, because when you read these problems and you hear constant velocity, that means there's no acceleration. Well, guess what? That simplifies his equation really fast. Okay? Or if it says, no acceleration or there's constant velocity, boom, we know what's going on. All right? We also describe this as what? It doesn't say this here, but this is also known as the law of inertia. Which is what? Anybody remember what inertia is from high school? Okay. All right. You're close. Yeah. All right. Has anybody ever been in a car and you go around a really sharp curve and you're going kind of fast and you notice you lean towards the curve? What do you do when you're on a motorcycle and you go through a curve? Do you lean into the curve? Do you lean to the curve, or do you lean the other way, opposite the curve? You better lean opposite, or you're going to have a fence post down your throat, right? Or somewhere else. Let's not go there, right? Yeah. Yeah. Why?
Except for a motorcycle?
Or a motorcycle, yeah. Why do you lean? Mm-hmm. Because what do you do? All right, now let's see if you remember chapter 3. What does a curve do when we're at constant velocity? What do we do in a curve? We do what? Very good. Hallelujah. See, y'all learn more than you thought you did. You accelerated. Just, why didn't I remember it for the test, right? Yeah, okay. Oh, come on, y'all. Y'all going to be okay. I got all the confidence in the world in you. All right. You accelerate. I know so. Well, I'm glad you do. Well, I do. You're going to make it, I'm telling you. Okay? You're going to make it. All right. Just got to keep working hard. And you will. I know you will. All right. I believe in you. All right. Now, okay? So we accelerate, don't we? All right. What am I doing when I go through that curve? What's my direction doing? All right. I'm pointed this way when I get into the curve, but then all of a sudden, my motorcycle's, I'm having to do what? I'm changing direction, right? Well, now, wait a minute. When I was going into the curve, my body was going this way, but the motorcycle says, no. We got to go that way. Right? Because of the curve. Okay, y'all. Same thing in a car. You're in a car, riding along. We used to do this. We used to triple date. Did I tell you about my buddy and his 56 Chevy? Have I told y'all that? You ever heard of COD and SOB curves? You ever heard about them? COD, SOB? I'm not cussing, all right? Okay, don't think I'm cussing. Well, Mr. Jill's cussing today in class. No, I'm not cussing, all right? All right, he had a 56 Chevrolet, and that thing was awesome, man. It had pop-up pistons, 3/4 cam, 850 dual line Holley. Man, I mean, it would fly. It's a tank, but it'd fly. You needed that motor for a tank. And I loved that old car, 56 210, Del Rey, all right. And it had bench seats in it before he put bucket seats in the front. You know, those things are huge. So you could triple date. We would triple date. 4 of us in the front and 2 in the back. And so we'd go out to eat and go to a movie or whatever, and I'd say, man, we'd go riding around, and I'd say, hey, go down past Valmonte. Y'all don't even know where I'm talking about. Top of the river. There used to be a steakhouse down there called Valmonte. And you go over Wythe Drive, and it's real curvy through there. You know where I'm talking about? It comes out at East Lake in Gunnersville. You know what I'm talking about? Real curvy. Most of those curves are like 25-mile-an-hour curves, 30-mile-an-hour curves. We'd hit them at 45. Because, that car wasn't going to come off a road. It was like a tank. It was like, what, 2 tons nearly? It was every bit of 2,500, 3,000 pounds. So, and whoever's in the back was going for a ride. Because, man, you'd hit that first curve, and if you were over here on this side of the car, all the way across that back seat in that car. So my buddy, Todd, he nicknamed them COD curves, come over darling, or SOB, slide over baby. So that's what we call those. And yeah, that's right. And then we'd hit the next one, then we'd slide all the way back across. So, if Sweetie was ticked at me, I'd say, hit the curves, man. I want her close, Bam, So, anyway, not really. All right. Not really. Not really. But anyway, all right, we'll just leave it at that. But anyway, I've done lost my train of thought. Y'all have done got me all tore up. Anyway, so that's inertia. I said all that to say this, that's inertia. That's inertia. Resistance to change in motion. Resistance to change in motion. All right, so let me write it here. Inertia is what? Resistance. I have to give a little bit of sauce for the poison. A little bit of sugar for the poison, make it go down better, right? Resistance to change. You finally described physics right, Mr. Shields. All right. Resistance to change in motion. All right? So your body reacts to that change in motion. And boy, I tell you what, if you're not paying attention, bam, your head hits the glass on the car, All right? Or you slide, and I am serious, y'all. I was not like this when I was in high school. I was not this big. I was tall, but I was real skinny. I'm talking beanpole skinny. I was 160 pounds and this tall when I graduated high school. Now I'm a whole lot more than that. Okay. And she better be glad because I'd have killed her. I'd have squashed her flat when I slid across that back seat. Anyway. And I'm not kidding. I'd slide all the way across that back seat. Anyway. Y'all think I'm kidding, but I'm not, all right? Well, it was crazy. Anyway, we were nuts. We had Ticklebelly Hill over here on Bruce Road or Brock Road. I think it's Bruce Road. Coming back this way, if you run about 40, 45 mile an hour, you come completely off the ground. Completely. Dukes of Hazzard. Yeehaw! Completely off the ground. I did that in my Camaro. I had an old Rally Sport Camaro. Did that several times. I did that one time on a date. Man, I thought she was going to kill me. Anyway. You're going to get me killed! I'm like, oh, that's fun. Roller coaster. It's like being on a roller coaster. I love roller coasters. But anyway. Yeah. Ticklebelly Hill. That's what we called it. Ticklebelly Hill. That's right. Oh, my Lord. I am telling y'all stuff. Anyway. Oh, my Lord, help me. But that's true. Inertia. There was another good example of inertia. Body resists change in motion. Your body comes off the seat. Okay? All right. Please don't try that over there. I don't want to come to no funerals, all right? So, okay. All right. So, yes. Who said Miss Shields? Oh. Oh, okay, yeah. Yeah, I don't want you to get hurt, all right? So, we have inertia. The body resists a change in motion, which goes right along with, you don't have to write this down, just listen, which goes right along with Newton's first law. Because his first law says what? Well, it says that little object right there is going to sit there and sit there and sit there until an outside force, is another way to define it, acts on it. In other words, it's going to remain at constant velocity, 0, 0, 0, 0, until outside force acts on it. And its constant velocity went from 0 to whatever, real high, fast. Okay? And that is also inertia. Notice its resistance to change in motion. When I grabbed it and did that, I felt it try to come out of my hand, so I have to increase my grip. That's why you grip things. You ever thought about that? When you're holding on to something, and if it changes motion, if you change your motion, or if you're throwing a football or trying to hang on to a baseball and throw it properly, if you don't hold it properly, inertia will give you the wrong motion, and you hit the pitcher in the head or something, or the guy batting in the head. Yeah, let me get it right. Yeah, we don't want to do that, because then we got to fight, right? Okay, now, so his first law basically says what? That when we are at equilibrium, this is all just a bunch of fluff, talking about acceleration. When we are at equilibrium, we are at constant velocity, whether it's sitting still or whether it's moving. We can be moving, okay, constant velocity, and then all of a sudden we change. Well, that resistance to change is inertia. Okay. All right. I really wanted to get to Newton's second law, but I don't know if I'm going to have time or not. Okay, again, second law. And we'll just start on second law today, and I'm going to give you a couple of 2 or 3 problems to look at. And we do have lab today, by the way. We're probably going to do the projectile motion lab. Okay. Newton's second law. His second law is built off the first in that, all right, we got constant velocity, no force. All right? No force. We're at equilibrium. Whether we're moving, spacecraft moving through space, constant velocity, until we hit the rockets. Then we get a force because we get acceleration. Then Newton's second law comes into play. We hit the rockets. All right, we feel that pulse. We feel that acceleration. You're driving along interstate, cruise control set. You're at constant velocity, no force. You hit the accelerator, you feel a force because you accelerate. Second law. That is the acceleration is the force. So his second law simply put that the force is what? Directly, I don't need to write it because it's written for you. Directly proportional to the acceleration and inversely proportional to the mass. You better remember that. So, if I want to double my acceleration of an object, if I want to double the acceleration of this chair when I push it, what have I got to do to the force? Got to double it. That's right. Why? Because it's directly proportional. Right? What if I double the mass and keep the, all right, I take it, push it with a force of, I don't know, 1 Newton. All right? Then I double the mass and I push it with the same acceleration. What happens to my force? It's halved. Did you get that? Same acceleration, double the mass, push it. I only have half as much force. Right? Ooh, yeah, we've got to be careful. Got to keep our thinking straight, all right? Now notice the units. Please, y'all write these parts down. That is so important to remember what a Newton is. Yes, we named it after him. My Lord, we should have named it after him. Are you kidding me? All right? Y'all, he did so much to change our world. People don't realize what kind of person he really was. Most people don't know he taught Sunday school. He taught Bible. He taught Bible lessons in his church. He was a big, big studier of the Bible. He studied prophecy like crazy. He knew there was a code to the Bible. Now, this is not going to be on test, but I got to tell you this because you don't ever read it in a physics book. He knew there was a code to the Bible, and he tried to figure it out, but he never did. It wasn't really discovered until the late 80s. Looking at the Hebrew, really interesting. And you never hear that about Newton. You never hear that about him. A lot of these guys, and by the way, he was a creationist. He believed in creationism. And a lot of these early scientists, and you never hear that about them, were creationists. And again, I'm not throwing stones at anybody, and you it's for America, it's a free country, and I don't think nothing less of you. You believe in evolution, okay. All right? That's fine. I don't think nothing less of you, okay? But I'm just telling you, okay? You never hear that. You never hear that on a program on TV hardly. Okay? All right. Anyway, I have to always throw that in there because he deserves it. My Lord, he developed calculus. Are you kidding me? He dadgum right, he deserves it. Pretty much did anyway. Whew, that just makes me want to go, ooh, every time I think about it. Okay. So please get this unit. Notice it's a kilogram. Now what does that mean? That means if we apply, let's say this chair, boy, I love using this chair. Y'all, well, hey, it's easy, y'all. Look, if this chair weighs 1 kilogram and I apply an acceleration of 1 meter per second squared to it, then we have a force of 1 Newton. That's what that means. You with me? You with me? All right. Okay. And by the way, we're not going to leave kinematics. We will still have to use some of those equations, but don't fret. It's not going to be too bad, I hope.